and welcome to the second video accompanying lecture 27. In the second video, and second of two videos, we are going to discuss radioactivity. All right, this is going to be a key characteristic that we're going to focus on here of the nucleus. In fact, we will discuss more about binding energy and the energy of the nucleus in the last chapter of this textbook, chapter 30, including nuclear energy, fusion, and fission. Now there's a kind of a fine line there, a blurry line between where radioactivity ends and nuclear fission and fusion begins, to some extent. I mean, there's a lot of the same ideas. But here, in this chapter, and in this video, we're going to discuss radioactivity. There's three types of radioactivity, there's some major applications of it, and that's going to be our entire discussion. And there's some kind of health considerations we want to know. All right, so that's the information you need to know. And then, of course, this will be relevant to the numerical questions that you can look at in lecture 28. All right, so let's get to it. All right, so in 1896, Becquerel accidentally discovered that uranium salt crystals emit an invisible radiation that can darken a photographic plate. All right, even if this plate is covered. So after several such observations under controlled conditions, so in dark rooms, Becquerel concluded that the radiation emitted by the crystals was of a new type, right? One requiring no external stimulation. The spontaneous emission of radiation was soon called radioactivity. After that, experiments by other scientists showed that other substances were also radioactive other than uranium salt crystals. Okay, and the most significant investigation of this type was conducted by Marie and Pierre Curie after several years of careful and laborious chemical separation processes of tons of pitchblende, which was a radioactive ore. The Curies reported the discovery of two previously unknown elements. So these are new radioactive elements that had remained hidden until this time. All right, because they're mixed with other minerals in very trace amounts. These elements were named polonium and radium. Experiments suggested that the radioactivity was the result of the decay or disintegration of unstable nuclei. So this was a big turning point. This was a new saga in human history, the discovery of radioactivity. Okay, so as I said, there's three types. So three types of radiation can be emitted by a radioactive substance: alpha particles, beta particles, and gamma rays. Okay? So what are they? So beta particles, I'll start with alpha particles. Alpha particles are the helium nuclei. They're ionized helium, so the helium without the electrons. Beta particles are electrons or positrons. There's two types. And gamma rays are just that. They're rays of photons. All right, the term ray used for light, right? Okay, and that term positron refers to a particle similar to an electron in all respects, the same exact mass, but having a positive charge, an inherent positive charge rather than an intrinsic negative charge. The positron is said to be the antiparticle of the electron. So if you heard that term antiparticle, that's what it refers to. It's opposite charge. So an antiproton would be a proton equal in mass, but with a negative charge. Okay? So we can distinguish these three forms of radiation by using the scheme described in the figure. The radiations the radiation from a radioactive sample is directed into a region where a magnetic field, where there's a magnetic field, and the beam will split into three components, two being in opposite directions, those are the charged components, and one not being deflected at all, which is the not charged component, the photon. Okay? There we can conclude that the undeflected ray is, of course, the gamma ray, carries no charge. The component deflected upwards contains positively charged particles. Those must be the alpha particles. And the component deflected downwards must contain electrons, the negative charge. All right? And if it's a positron, then it would be deflected upward in the same direction as the alpha particle. But its different mass would give it a different radius of circular motion in our uniform magnetic field. And we can use the right-hand rule to make that connection. And excuse me, I didn't realize I hadn't flipped to the slide. Okay? So everything I was just talking about is referring to this figure here. All right? And again, you can use the right-hand rule with the magnetic field going into the board to determine the direction of deflection for the positive charge, for the negative charge, and for the no charge at all on the photon. Okay? All right. So that's the kind of the first synopsis. We'll talk a bit more about alpha particles, beta particles, and gamma rays, the three forms of radiation, in just a couple slides. But again, the big thing to remember is some are positive, some are negative, and some are uncharged. Or maybe you can just think of them as One is 2 protons and 2 neutrons, one's a photon, and one's an electron. All right? So just remember which are which. Okay, there. So switch the slide this time. Okay, so the decay constant and half-life. All right, so moving on to kind of introducing the big things that we need to know as we move forward. All right, so one of those is that a radioactive sample containing n radioactive nuclei at some instant in time, well, as that sample decays, it will have a changing number of nuclei, a delta n. The decay in a small time interval, delta t, is proportional to n. This can be written mathematically as shown, where lambda represents a constant that is called the decay constant. The decay constant, okay? And I'll talk about this more when I talk about the key equations. The negative sign signifies that n decreases with time. It's decaying. The sample is decaying. That is, delta n is negative, so the change in n is always negative. The value of lambda for any isotope determines the rate at which that isotope will decay. The decay rate, or activity R, of a sample is defined as the number of decays per second. Okay? So R is the activity. It's change in number over time. All right? And so that would be equal to the decay constant times n. All right? All right? So that is the relationship. That's that's our our equation. And the units that I wanted to make clear, if we think about this, right, this is number, so this is just unitless, this is counting. This, of course, is time measured in seconds. So that means that the decay constant is also a unit of time. Okay? And so our activity then is going to be, let's see, so actually we have, this should be n times delta n times n. The decay constant, is inverse seconds. All right, because we have to have our units cancel out because our delta S is measured in seconds. So decay constant is inverse seconds right here, right? So the units are 1 over seconds, or seconds to the negative 1. All right, good. Okay. So for this equation, you can see that isotopes with a large decay constant decay rapidly. Those with a small decay constant decay slowly. A general decay curve for a radioactive sample is shown in the figure, right? So it's going to have this shape. It is an exponential decay. It could just be a steeper exponential or a less steep exponential, depending on your value of lambda, okay? The number of nuclei present varies with time according to the equation, all right? So this is our decay. It's exponential decay. Okay, that's the mathematical form. All right. So that's going to lead then to the idea of the half-life. Okay, so often we use a parameter called the half-life to describe radioactive decay. The half-life of a radioactive substance is the time it takes for half of a given number of radioactive nuclei to decay. So we can use this idea to write the equation shown here. The number n can take any non-negative value and doesn't need to be an integer. Okay, it could be a fraction. Right now, here's our n. Okay, so this is the idea of the half-life. It's the instantaneous population is equal to the original population times 1/2 to the n power, where the n power is the time that's elapsed divided by the half-life. Okay, and this would be a fixed time that's often given. Okay, so if we solve for the half-life, all right, by working through, then we get to this step here, and this is just isolating t1/2 because that is a variable in itself. Okay, it's just t with a subscript of 1/2. And as we isolate it, going through, doing a natural log in order to get rid of our exponential, we eventually get that the half-life is just the natural log of 2 divided by the decay constant. All right? So the half-life is 0.693 divided by the decay constant. So you can then represent, or you could say that the half-life is representative of the radioactivity of the sample, and so is the decay constant. You don't need both, you need one or the other. Okay? Note that after an elapsed time of 1 half-life, half the initial radioactive nuclei remain. After 2 half-lives, half of those will have decayed, and 1/4 the initial radioactive nuclei remain. After 3 half-lives, 1/8 will remain, and so on. Okay, so now let's talk about the decay rate, or the activity rate. So the unit of activity R is the Curie, okay, defined as shown here. So one curie, this is the standard unit of radioactivity, is 3.7 times 10 to the 10 decays. All right, so it's 370 billion decays, or 37 billion decays per second. Okay, that's a curie. Now, there's also the becquerel, okay, if I'm pronouncing it correctly, and the most commonly used unit of activity is the millicurie or the microcurie. Okay, but the becquerel is nice because it's exactly 1 decay per second. It's just that it's a little too slow, right? Most radioactivity is going to be, for a reasonably sized sample, for a macroscopic sample, would be more on the order of curie, or perhaps somewhere in between, which gives us the millicurie, right? Because 1 millicurie is 1/1000th of a curie, so that would be 3.7 times 10 to the 7 decays per second, okay? And 1 microcurie would be 3.7 times 10 to the 4 decays per second, okay? So those are the ones that perhaps just have the most utility in terms of the units, okay? So, true or false? A radioactive atom always decays after 2 half-lives have elapsed. Right? You know the answer to this. Of course, it's false, okay? Because it's not like it's gone after 2 half-lives. That's not the meaning of half-life. That is probably a widely held misconception, but I think certainly we can quickly realize in this class and at this level that that's obviously not what a half-life means, okay? All right, so what fraction, right? Here's what it really means, the idea of the half-life. What fraction of a radioactive sample has decayed after 2 half-lives have elapsed? Well, you know it, right? So what fraction of the sample has decayed after 2 half-lives have elapsed? All right, so after 1 half-life, we have, right, 1/2 decayed. After 2 half-lives, all right, so, okay, so that should work out to be, yeah, so that should be 1/4, all right, so, or excuse me, 3/4, so 2. I was looking at my notes here. My notes have it for 3 half-lives, but the question asks for 2, okay, so after 2 half-lives, 3/4 has decayed. After 3 half-lives, right, if this was changed to 3, well then it would be 7/8 would have decayed, okay? All right, so suppose that the decay constant of radioactive substance A is twice the decay constant of radioactive substance B. If substance B has a half-life of 4 hours, what's the half-life of substance A? Okay, well, the answer is 2 hours, okay? And here's the question. So, excuse me. So the reason that the answer is 2 hours is because we have T 1/2 of A is the natural log of 2 over lambda A, okay? And then that's going to equal also the natural log of 2 over 2 of lambda B, because that's what was compared, was the decay constants of the two, all right? And so then if we want to then continue to solve for this, then we'll make our substitution in here. So then we would have that this is going to be equal to T 1/2 B over 2, which is just 4 hours over 2, or 2 hours, all right? So it is half the time, all right? So then, of course, 2 hours is our answer. All right, so now let's talk a little bit more about the 3 types of radioactive emission. So alpha decay, all right? So in a nucleus, or if a nucleus emits an alpha particle, it loses 2 protons and 2 neutrons. That means the neutron number n of the single nucleus decreases by 2. Z decreases by 2 and A decreases by 4, right? So the decay can be written symbolically as shown, right? So we see A goes down by 4, Z goes down by 2. That implies that n also goes down by 2. It doesn't show up in the notation because you can always calculate n from knowing a and z. And why does it go down? Because you have to have enough nucleons, 2 protons and 2 neutrons, to make a total of 4 nucleons for your helium nucleus. Again, helium without an electron. Ionized helium, effectively. Okay? So the decay can be written symbolically as shown, as I said, where X is called the parent nucleus and Y is the daughter nucleus. Okay? As examples, we have uranium-238 and radon-226 are both alpha emitters and decay according to the scheme shown. All right? So the half-life of uranium-238 is about 447 billion years, and the half-life for radon-226 is 1,600 years. All right. In both cases, note that the mass number A of the daughter nucleus is 4 less than that of the parent nucleus, and the atomic number is reduced by 2. The difference are accounted for in the emitted alpha particles. All right. So uranium becomes thorium, and radon becomes whatever rad is. Okay. So, excuse me for not knowing the element name. I often forget them, but we can always look them up on the periodic table. Now, I mean, so the thing to remember is that with alpha emission, the element that is created, the daughter nucleus that is created, will always be 2 spots down the periodic table, okay? Because the periodic table is determined by the number of protons, and the number of protons only changes by 2, even though the number of nucleons changes by 4 with alpha decay, okay? So this is just a schematic showing the alpha decay, all right? So the decay of radon-226 is shown in the figure. When one element changes into another, as happens in alpha decay, the process is called spontaneous decay or transmutation. As a general rule, the sum of the mass number A must be the same as both sides of the equation, and the sum of the atomic number Z must be the same on both sides of the equation. They must be conserved. For alpha emission to occur, the mass of the parent nucleus must be greater than the combined mass of the daughter and the alpha particle. In the decay process, the excess mass is converted into energy of other forms and appears in the form of the kinetic energy of both the daughter nucleus and the alpha particle. All right. Most of the kinetic energy is carried away by the alpha particle because it is much less massive than the daughter nucleus. And we can understand this because the particle's kinetic energy and momentum are related. All right. So we can see here, this is our relationship between kinetic energy and momentum. Right? Kinetic energy and momentum P. Because momentum is conserved, the 2 particles emitted in the decay of the nucleus at rest, right, must have equal but opposite directed momenta. As a result, the lighter particle with the smaller mass in the denominator must have more kinetic energy. All right, so it's simply a matter of classical mechanics that tells us that the alpha particle will always have more kinetic energy, and it's going to be moving much faster than the daughter nucleus, right? But more than just moving faster, it actually has more of the overall energy goes here. Okay, so interesting that we can make that conclusion about these fundamental particles just using classical mechanics, but it really works quite well as long as they're not moving at relativistic speeds. Okay, then obviously we would need relativistic kinetic energy and momentum. All right, okay. So there has to be a net energy gain. It's not this idea of spontaneous emission. So radioactive elements like uranium and radon that we talked about historically, they have to happen spontaneously because it's energetically favorable, something we'll talk about called the Q value in just a moment. And so in doing so, it's got to be, there has to be that idea that there has to be a tipping point. That means that lighter elements aren't going to have spontaneous alpha decay. They would be at a loss of energy actually by emitting an alpha particle. But large elements can have a net gain of energy, and that excess energy becomes the kinetic energy of the products, right? As we see, because they have velocity. Okay, so let's move on to the next type of decay, beta decay. So when a radioactive nucleus undergoes beta decay, the daughter nucleus has the same number of nucleons as the parent nucleus. Okay, so the number of nucleons doesn't change, but the atomic number is changed by 1. As you can see in these two reactions, again, note that the nucleon number and the total charge are both conserved in these decays, right? Charge and particle type are conserved. As you will see in a few minutes, these processes are not described completely by these expressions, okay? There's something else we're missing. A typical beta decay event is shown here, all right? This is a carbon becoming nitrogen and an electron. You might be surprised by the emission of electrons from a nucleus, right? Because the nucleus is composed of protons and neutrons only. How this works is that the electron is emitted when a neutron is transformed into a proton. All right? So this is the representation of the process. So it's a neutron becoming a proton plus an electron. And here we're using the notation like we would for the nucleus, but we're using that notation specifically for nucleons. It's a kind of a common extension of this notation that we use for the nucleus. Okay? All right. And of course, this notation can have added pluses or minuses that talk about the electrons. So it's a very versatile notation. But we do see, right, that with our two types of beta decay, with beta minus decay here, as it's called, we have the proton number, the atomic number, go up by 1, because now we have one more proton than we used to have because one of the nucleons became a proton and emitted an electron. On the other hand, we can have beta plus decay, where we have a positron that is emitted. And in this case, we have essentially we're having an extra neutron created, okay? But beta minus is by far the more common, and this is the type that we're going to talk about, okay? More about beta decay. So the energy released in the beta decay of carbon-14 is approximately 0.16 mega electron volts. As with alpha decay, we expect the electron to carry away virtually all of this energy as kinetic energy because it is the lightest particle produced in the decay, and even a much more dramatic comparison in mass than the smaller alpha particle compared to the daughter nucleus. Here, we're going to have the electron be really tiny and carry away almost all of the energy. If we take a look at the figure here, which shows only a small number of electrons having the maximum kinetic energy, represented as kinetic energy max in the graph, most of the electrons emitted have kinetic energies lower than the projected value. So if the daughter nucleus and the electron aren't carrying away this liberated energy, where is it going? As an additional complication, further analysis of beta decay shows that the principles of conservation of both angular momentum and linear momentum appear to have been violated. All right? So unlike with alpha decay, where we can fully explain energy and momentum by having the alpha particle decay, we have a serious problem here. We have these beta particles, these electrons, not carrying away enough energy. So what's going on, right? Well, the fact that angular momentum and translational momentum aren't conserved leads to the discovery historically in 1930, where Pauli proposed that a third particle must be present to carry away the missing energy and to conserve the momentum. Later, Enrico Fermi developed a complete theory of beta decay and named this particle the neutrino, the little one, all right? Because it had to be electrically neutral like a neutron and have little or no mass. Although it eluded detection for many years, the neutrino was finally detected experimentally in 1956, all right? And so the characteristics of the neutrino are that it has 0 electric charge, has a very small mass, smaller than an electron, it's spin 1/2 like an electron, and has very weak interaction with matter. All right, and there's a lot we can talk about the neutrino. It being one of the first more exotic particles, hard to detect particles, historically speaking. It has been heavily studied, and it's very important. And maybe these other more obscure particles that we'll talk about briefly in lecture or in chapter 30, like pions, and so on, or even muons. Maybe there's more to them than has been published and so on, or is widely known. But the neutrino, as I said, is just so fundamental. It's our window into our sun. It's one of the fundamental ways that we explore what's going on in the core of the sun, and really the only way. And it just is a major player in particle physics. All right, but let me move on. Okay, so with the introduction of the neutrino, we can now represent the beta decay process in the correct form as shown here. The bar in the symbol indicates an antineutrino, right? That's what this is right here. This is called an antineutrino. Why an antineutrino? Well, because the antineutrino has to have the positive charge, okay? So let's see if we can understand what an antineutrino is. First, let's look at the decay, all right? And here we see that with nitrogen-12, or when nitrogen-12 decays into carbon-12, a particle is produced that is identical to the electron, except that it has a positive charge of plus E. The particle is called the positron. Because it is like an electron in all respects except charge, the positron is said to be an antiparticle of the electron. In beta decay, an electron and an antineutrino are emitted, or in this case, a positron and a neutrino are emitted. So there always has to be one particle, such as an electron, and one antiparticle, such as an antineutrino. But when there's an anti-electron, then there is a normal neutrino. Of course, it turns out that antineutrinos are going to be the more common produced because electrons are more commonly produced through beta decay. So that's kind of interesting, right? So like unlike beta decay, which okay. So here we have the number of alpha particles. Okay, so the observed energies of alpha particles are discrete, having only a few values, right? So unlike alpha decay, which results in daughter particles with a variety of possible kinetic energies, it's the ones shown here. Beta decay comes in, unlike, I should have said it correctly the first time, unlike beta decay, which results in a daughter particle with a variety of possible kinetic energies, alpha decay comes in discrete amounts, as you can see in the figure. This is because the two daughter particles have momentum with equal magnitude in opposite directions, and are each composed of a fixed number of nucleons. Okay, so this is final comparison between alpha decay and beta decay. Okay, so now let's briefly talk about the last type of decay. So often a nucleus that undergoes radioactive decay is left in an excited state. So as a result of a kind of a following consequence of either of the decays we just talked about, alpha decay or beta decay, so the emission of a helium nucleus or an electron, the leftover daughter nucleus is excited. It's in an energy state, just like an electron can be in a state that's other than the ground state. Nucleons and the nucleus as a whole has a ground state as well and has excited states above that ground state. Okay. So the nucleus can then go a second decay to a lower energy state, perhaps even to the ground state, by emitting one or more high energy photons. They're high energy photons because the states are it's a very, very deep well of potential energy. And so the energies are quite large compared to the electrostatic or the electrodynamic potential energy well of electrons bound to the nucleus. The nucleus itself is bound together with much larger energies. All right? And so that is the production of gamma rays, all right? And so those gamma rays, again, are high energy photons, and we represent them as so. Right here is a decay that is a beta decay. This is standard beta decay, where an electron is emitted along with an antineutrino, and that's going to leave. We can see here that this notation denotes the excited state that the carbon is left in. So our carbon-12 is left in an excited state. So immediately afterwards, right, within some number of nanoseconds or picoseconds, the excited carbon is then going to decay into unexcited carbon plus a high energy photon. And there are ways to quantify, exactly how high energy that is. It's shorter than X-ray, or sometimes gamma rays are X-rays. Just high energy X-rays is kind of a continuum, the naming there. But the point is that they're very, very short wavelength, very high energy particles, right? So, okay. All right, so quick application here. We have the idea of smoke detectors. So smoke detectors can work on detection of radioactivity. So as long as the current is maintained here in our circuit, then if the smoke drifts into the chamber, the ions become attached to the smoke particles, and these heavier particles that do not drift as easily as the lighter ions, and then what happens is then the current is decreased, and that sets off the alarm. Okay, so kind of quick synopsis there. All right, I'm going to skip over radon detection for now, but you can read it on your own. I want to get into carbon dating because we still have some quick topics to cover. This is just going to employ the idea of the half-life. All right. So to use radioactive dating techniques, we need to rewrite some of the equations that we saw before when we introduced the decay constant. So let's start by multiplying our decay equation by the decay constant. All right. So we can then rewrite it like this, okay, where we have our rate. All right. So if we then substitute this expression, where R is the present activity and R naught is the activity when the object began, maybe when it was living, because that's the idea with carbon dating, is there's a fixed amount of a certain isotope once the organism stops living, it stops absorbing that isotope from the external environment, and so then the population of that isotope decays. All right, so then we can take the natural log of both sides, like so, and then we're left with an equation for t, which will just be the age of the sample. All right, now of course you could have done this process yourself, but if you want a ready-made equation that gives you the age of a sample, then you have it right here. Okay, and all you need to know is the current activity and the initial activity. And the initial activity would be a known quantity that would be published. Okay, so radioactive nuclei are generally classified into two groups: unstable nuclei found in nature, which give rise to natural radioactivity, and those that are produced in a laboratory. So the nuclei that are produced in a laboratory that exhibit artificial radioactivity. So these series, three series of naturally occurring radioactivity nuclei exist, as shown in the table here. Each start with a specific long-lived radioactive isotope with a high life or half-life greater than any of its descendants. The fourth series in the table begins with neptunium-237, a transuranic element, which is an element having an atomic number greater than that of uranium. The element is not found in nature and has a half-life of only 2.14 million years. Okay, so this is a unnatural element right here. Okay, looks good. So thorium-232, the thorium-232 series is shown in this figure. The two uranium series are somewhat more complex than thorium-232, but this one can clearly be shown, and we can see the ultimate product of this result. All right, and also there are several other naturally occurring radioactive isotopes like carbon-14 and potassium-40 that are not part of either decay series. Right, so these would be kind of additional series, although kind of what is the literature called the traditional series seems to be up for debate. So natural radioactivity constantly supplies our environment with radioactive elements that would otherwise have disappeared long ago. So, for example, because the solar system is 5 billion years old, the supply of radon-226 with a half-life of only 1,600 years should be complete. It shouldn't exist, right? However, it does because uranium-238 is constantly replenishing the supply. All right. And uranium-238 has a half-life of 4.47 billion years. Plenty long to still have a significant amount left, and thus replenishing the supply of radon-226. Okay? All right, so in nuclear reaction, it is possible to change the structure of the nuclei by bombarding it with energetic particles. So you can change a particle into another type as long as the number of protons and neutrons is conserved. Okay? This is like a transmutation of particles. We just have to have our bombardment be fast enough that we're overcoming the repulsive energy between between the protons and between the nuclei themselves. Okay, so then we can produce new elements through high energy environments, new particles. Okay, so which of the following are possible reactions? Okay. So we look here, we want to conserve the total charge and total mass number. That's absolutely required. So reaction C violates conservation of mass number and the sum of mass numbers being 240 before the reaction and being only 223 afterwards. But A and B are possible, okay? So that means that 2 is the correct answer. Only C is the impossible one because the idea is that we don't add up to the right number, okay? So before we have 240 nucleons, afterwards we only have 223. If we add these numbers together, they just don't add up enough. Even if we take the 3 times the 1, it becomes on this side over here is only 223. And obviously we need 240. So that can't happen. Okay, we can't have a disappearance of these nucleons. Okay, they can leave as an alpha particle, but they can't just simply cease to exist. Okay. So now quickly the idea of the Q value. So if we turn our attention to the energy involved in nuclear reactions, energy, as you know, is an important quantity that must be conserved. So if we analyze the nuclear reaction shown here, excuse me, the total mass on the left side of the equation is the sum of the masses of 1 deuterium and 1 nitrogen-14. Okay, so there is, we have a change in mass. As you can see, the total mass before the reaction is greater than the total mass after the reaction. Okay. Good. All right. And This lost mass is converted into the kinetic energy of the nuclei present after the reaction. The energy required to balance the equation is called the Q value of the reaction. For this reaction, the Q value is 13.56 mega electron volts. Okay? So here we see, right, that we have a certain amount of atomic mass on one side. That would be on the right side. All right, that's over here, and it's less than the atomic mass we started with, right? And so that amount of mass is equal to that amount of energy. Okay. So nuclear reactions in which there is a release of energy that is a positive Q value are said to be exothermic, right? So that's when the mass goes down. That would be an exothermic reaction. Okay. The energy balance sheet is incomplete, however, because we must also consider the kinetic energy of the incident particle before the collision. Because here, this wasn't a spontaneous emission. This was crashing together a helium atom and a nitrogen atom. Okay. So as an example, we can assume that the deuterium had a kinetic energy of 5 mega electron volts. If we add this to our Q value, if we add this in, then we see that our Q value is actually 5 mega electron volts larger. So instead of being 13.57, it is 18.57. Okay, or 58 if we round. So we can also consider a reaction like this, where we have, okay, so let's go through it. So now let's consider the reaction shown here. Before the reaction, the total mass is going to be the sum here. All right, so this is on the left-hand side, and I'll get back to the other numbers in just a second. But on the left-hand side, we have an initial total mass of 18.005 atomic mass units. On the right-hand side, our final mass is 18.006. Why is that? Well, because we conserved the number of nucleons. This is a possible reaction. But what happens is we have the mass going up. Okay, so mass is increased. If the mass is increased, then we have a delta M that is given as so, and that gives us a negative Q value. Okay, and with our negative Q value, that means that we have an endothermic reaction. Okay, and the endothermic reaction means that it requires an input of energy. All right, so it doesn't produce any energy. So this means that the incoming particle must have at least enough kinetic energy to overcome the energy deficit. And that means that we have, if we think about the kinetic energy of the incoming particle, it must have at least 1.535. Okay, so you might think this equation can occur if the incoming, let me clarify where that number comes from, might occur if the kinetic energy of the incoming particle is the exact lost energy, the deficit of 1.194. In practice, though, the alpha particle must have more energy than that. If it has an energy of only 1.194, then yeah, energy is conserved. But when we look at the reaction in terms of the momentum conservation, we see that the incoming alpha particle has some momentum before the reaction. If its kinetic energy is only 1.194 mega electron volts, the products oxygen and a proton, okay, in other words, maybe an ionized hydrogen, would be created with zero kinetic energy, and so zero momentum, which is not possible, right? So sure, yeah, the minimum amount of kinetic energy would end with them both at rest, and that would satisfy the deficit, but momentum wouldn't be conserved. Thus, in order for momentum to be conserved, our equation is this, okay? All right, so let's wrap this up with a couple more slides. So to try, let's take a look at an example here. So the Q value of an endothermic reaction is negative 2.17 mega electron volts. Then the minimum kinetic energy needed in the reactant nuclei, if the reaction is to occur, must be what? Well, we might think, well, to overcome the deficit, yeah, it's exactly, but we know that's not the case. It must be greater, right? So it's got to be at least a little bit greater than the 2.17, because we can't have the products of the reaction be at rest, because that would not conserve momentum. All right, so let's talk a bit about radiation damage, right? So we can have somatic damage, which is radiation damage to any cells except the reproductive cells, and we can have genetic damage, which is damage to the reproductive cells. These are the health concerns of radiation, which are often on people's minds. When we talk about radiation, there are actual units that quantify or attempt to quantify the health risks of radiation. One of those units is the Roentgen, and the amount of ionization radiation that will produce 2.8 times 10 to the 9 ion pairs in 1 cubic centimeter of air under standard conditions. Okay, that's 1 roentgen, if I'm saying that correctly. The amount of radiation that deposits 8.76 times 10 to the negative 3 joules of energy into 1 kilogram of air. Okay, those are equivalent measurements that would both quantify the roentgen. Okay, a rad, on the other hand, is the amount of radiation that deposits 10 to the negative 2, so basically just 1 centijoule, of energy into 1 kilogram of absorbing material. Okay, so those are the two common ways we talk about rads or roentgens. Okay, there's also the RBE, which is the number of rads of X radiation or gamma radiation that produces the same biological damage of 1 rad of the radiation being used. Okay, so this is the idea of comparing between gamma radiation and other forms of radiation. Okay, so we see that X-rays would then have an RBE factor of 1 because that's the standard. Beta particles, on the other hand, tend to be more damaging, right? Because we're talking about biological damage, right? So we see then that a beta particle has the ability to be almost twice as damaging. On the other hand, an alpha particle has the ability to be 10 to 20 times more damaging. A free neutron from a neutron source, which we haven't talked about, but some elements tend to be good neutron sources, 4 to 5 times more damaging, or 10 or 20, right, in the case of heavy ions being emitted. All right, so we can see that you can kind of compare to the light radiation, which can be damaging. Obviously, X-rays and even higher energy photons than X-rays can be quite biologically damaging, but these other more massive particles have even more potential to be damaging. Okay, and REM is the product of the dose in rads and the RBE factor. So a dose in REM is multiplying rads by RBE, so taking into account the biological, right? So it's accounting for that. It's an extra step. Okay, if we talk about kind of how do we stop radiation? Well, the idea is that radiation has a certain amount of penetrating power, and so you can stop gamma rays with a very thin layer. They're stopped, you can stop alpha particles with a very thin layer. They're very easy to stop, right? So the skin, for the most part, stops alpha particles. However, if an alpha particle contacts a biological cell inside because you consume the alpha particle, then it can be quite damaging, right? So low penetrating power, but high potential to damage if it's allowed to contact cells, okay? On the other, and then clothing also stops alpha particles very easily. A beta particle is harder to stop, but a very thin sheet of iron can stop it. Aluminum foil, for example, can stop beta particles. So they're potentially more damaging, but easier to stop. On the other hand, those gamma rays, which are the least damaging, also have the most penetrating power. So gamma rays can penetrate through many centimeters of concrete, and you need a thick wall of iron or many feet of concrete to stop a gamma ray. Okay. All right, well, I'm just going to go ahead and wrap it up. There's a couple of other applications here, but please take a look at the topic summary. It's an excellent way to see the overall summary of the chapter, and also check out the accompanying video for lecture 28, where I do some examples of radioactive half-lives and decay rates. All right, so thank you so much for watching.